Greetings. I'm going to redo a couple of videos that were problematic in terms of seeing the markers on the board in the physics lab. One of the things I discovered is that this computer I'm using now, coupled with the camera I'm using, doesn't seem to do a good job of reproducing those writing on the whiteboard, at least in the physics lab. So I will avoid doing that, and I apologize for the videos that didn't come out so well. So this one is going to be on the capacitor and on the volt. And the other videos that I was asked to redo from some of you are actually, I was able to recycle older videos that I've had that cover the same materials. So those are already up. Okay, so how I started this video originally was I asked you if you have these two planes, one with plus on the right and minus on the left, can we draw the electric field lines and lines of constant potential? So you can pause the video and try it. I will go ahead and do it right now. Whoops, I want to move my arrows. I created them, I put them here. And then I'll copy and paste them and put the next set down there. Whoops. And there we go. That's what the electric field lines would look like. They'd be emanating from the positive side and be directed to the negative side, as you can see there. Lines of constant potential, as we also have talked about, are going to be perpendicular to the electric field lines, and I'll draw those as perpendicular lines to them. They'll be parallel to each other in this case, because the other lines are parallel, so all the lines of constant potential will be perpendicular. Now, these are arbitrary potentials. Of course, there could be an infinite number of these, so I'm just going to be picking a select few to use in my drawing here. So those are going to be examples of lines of constant potential that I could draw here. The next slide, which you have also seen, summarizes the calculations for electric field and potential associated with a positive point charge and a positive plane of charge. So this is kq over r squared. That was the first thing we talked about when we started talking about electric field. And potential for a point charge is kq over r. Similarly, for a positive plane of charge, sigma over 2 epsilon 0 is going to be where sigma is the charge density per unit or per square meter, and epsilon 0 is the permittivity of free space. That's what the electric field strength is going to be anywhere at any distance away from a plane. Potential, on the other hand, will be that electric field times the distance you are away from that plane of charge. Now, when you have two planes of charge, which is what the next slide is going to show, two planes of charge, then the electric field from each plane of charge reinforces. So this, at the point where the star is, or actually at any point in between here, the electric field is going to be equal to sigma over epsilon 0, which I calculated here for you. You can do the calculation on your own. And the reason there's a negative sign there, negative I hat, is because the electric field is pointed to the left. And I'm hopeful that when I do that, you know that it's from plus to negative. Sometimes these cameras flip the direction in which I'm pointing. It might look like I'm pointing to the right, but I'm intending to point in the direction from the positive here to the negative on that side. All right. The other thing I could ask then is, let's calculate the potential between both between these two planes of charge, assuming the one with a negative charge on it is a potential of 0. What's going to be the potential of the positive plane of charge if they're separated by 1/10 of a millimeter? For that matter, what's going to be the potential at the point marked by the star, which is supposed to be smack in the middle of the two planes of charge right there? So we could do that. And the next slide describes that normally finding the potential involves an integral that we've talked about in the past. But when the electric field is uniform, when it's the same everywhere, that integral just becomes a product. So all we have to do, coming back here, is find the distance from 0 potential, and we're taking the negative plane here to be 0 potential, and multiply that distance times the electric field strength in between here. So the further away you are from it, the greater the potential will be. And that's what I do on the next slide. So I actually just do that calculation. Just take the E and multiply it times the D. Since E is the charge density divided by the permittivity of free space, as we talked about earlier, that's the electric field between two planes of charge, multiply that times the distance you are from the plane of charge that you're considering to be zero potential, and the result will be your potential at the point of interest, or at the distance of interest from the plane. So if I'm 0.1 millimeter away from the negative plane, that's actually at the positive plane of charge. I take the electric field strength that we calculated, which is the 1.13 times 10 to the 11th newtons per coulomb, and I multiply that times the separation, the D, which is 1/10 of a millimeter, which is 0.0001 meters. Always convert it to meters. All right, and then if I want to find the potential, and then I get my answer of 1.13 times 10 to the 7th Newton meters per coulomb. And I'll talk about that unit in a moment. And if I want to find the potential at the point of the star, that's 5/100ths of a millimeter away, or 1/2 of a 1/10 of a millimeter. So I take that value of distance here. Let me see. There should be an extra 0 in there. And I multiply 0.0005 meters by the electric field strength, and then I'm going to get 5.7 times 10 to the 5th Newton meters per coulomb. Great, it's just multiplication. But you're probably wondering, what the heck is a Newton meter per coulomb? That's what the next slide is going to show us. A Newton meter per coulomb, let's think about it. Well, a Newton meter, remember, force times distance is equal to energy. That's what we talked about in Physics 220. So if you push something with a certain amount of force over a given distance, that takes a certain amount of energy to do that. And that energy, the SI unit for that Newton meter, is a joule. So a Newton meter per coulomb, another way to express that, is a joule per coulomb. But a joule per coulomb represents the amount of energy it takes to move a certain amount of charge in a field. And that energy it takes to move, energy that required to move a certain amount of charge is also known as a volt. A joule per coulomb is a volt. So a Newton meter per coulomb is also a volt. So what we calculated in the previous slide could have been written just as volts. A volt is a Newton meter per coulomb. So it's another unit translation. We get a few of those, particularly in second semester physics, that come out of the blue. And you'll see some other ones that are really interesting and perhaps a bit unexpected. So that's what this next slide shows you. And this next slide will be, this slide deck, lecture 18 addendum, will be posted on the iLearn site for lectures. So you can look at this and look at these slides in more detail on your own if you like. Then the final thing I wanted to mention is how much charge was placed on each of the plates in the original problem. So going back to the original problem, which was up here, I said that each of the charge density on these plates is 0.1 coulombs per square meter. So how many coulombs had to be placed on these plates to generate that charge density? Well, remember, charge density is given by this equation. Sigma, which is the charge density, is equal to the charge, total amount of charge on one of the plates, divided by the area of that plate. So if I convert the area, which is 100 square centimeters, that's what's given in this problem, convert that to square meters. Don't forget you have to multiply twice by the conversion of a meter is equal to 100 centimeters. So I have two of those conversions here. That is going to give you a result of 1/100th of a square meter as the area of one of the plates. Then if I take that area of the plate and multiply it by the charge density that's given in the earlier problem, then I'm going to get the overall charge. And that charge is going to be 0.001 coulombs, because what I'm multiplying is the 0.01 square meters by the 0.1 coulombs per meter squared. That gives me 1/1000th of a coulomb. So one of the plates is going to have 1/1000th of a coulomb positive, the other one will have negative 1/1000th of a coulomb. That's what's meant by the charge on the plates. Both plates have an equal and opposite charge, so they're actually net neutral. This actually covers what the lectures that you had trouble seeing, two of them anyway, with those covered, and the other two lectures are covered by earlier lectures. So I think we're good, and I will see you again on Thursday. Of course, email me if you have any questions, and I will respond as quickly as I can. Take care.